I welcome you for this session on slope deflection method. In the previous session, we have discussed in this session also we will continue with the slope deflection method and we're going to apply this for a continuous beam. Now we are taking a numerical example of a continuous beam. We are supposed to use slope deflection method and where the support B is sinking by 5 mm and the flexural rigidity of the B member is been given as 2 into 10 power 4 kilonewton meter square. We have a two span beam. Along with that we have a overhang, and we can identify two major differences from the previous problem, and this is that at joint B we have a settlement of support or sinking of support by 5 mm, and we have a overhang portion as well. So now these two needs to be taken into account while we are analyzing. Now this sinking of support which has been given as 5 mm, so which will going to induce bending moment at the different joints, that is has to be considered in while writing the slope deflection equation, and the value of 3 delta by L, which actually represents the moment because of the sinking of support, wherein the value of delta needs to be calculated. We'll see that a little later. Now coming to the solution, the first and foremost thing which we are required to do is that we are required to write the fixed end moments. We will calculate the fixed end moment at all the joints for different spans. At joint A for span AB is MFAB, which is equal to minus WAB square by L square, as it is eccentrically loaded. A is 3 and B is equal to 2. So we get MFAB as minus 28.8, as it is creating a negative bending moment. So we are taking it as anti-clockwise, we are taking it as negative. MFBA is positive, it is in the clockwise direction. W A square B by L square, which works out to be 43.2 kilonewton meter. And similarly, for the second span, which is subjected to a concentrated load, which is acting at the mid span, and at joint B we have a anti-clockwise moment which gets generated. So we take it as negative minus WL by 8, which is minus 80 into 4 by 8, which works out to be minus 40 kilonewton meter, and MFCB, which is also equal to 40, but it is in the opposite direction. It is plus 40 kilonewton meter. So now we have calculated all the fixed end moments at joint B, A, B, and C. Whereas at C we have another moment at this joint which is acting in this direction. This is a reactive moment again, which is because of this uniformly distributed load which is acting. Now this uniformly distributed load for the cantilever portion which is acting is, I can directly write that the value of the bending moment which is at joint C because of span CD, which would going to be equal to, since it is a cantilever portion, because of the application of the UDL, it will go into Hawk. So I'm taking it as negative. And the magnitude of the bending moment, I can take it as W into L by 2. I can directly take it as L square by 2. So which works out to be equal to minus 20 into 2 square by 2, which works out to be also equal to minus 40 kilonewton meter. So we can apply this condition that MCD is equal to minus 40 kilonewton meter. It's not a fixed end moment. I'm directly writing the bending moment at that joint for span CD as MCD directly I'm writing. So that's what I've written it here. Now we'll go with the application of slope deflection equation. Now we'll go to apply slope deflection equation for span AB. Now we know that span B is sinking by 5 mm. Now what happens is when it sinks, I'll take, this is the new position of the beam. Now there has to be a moment which gets generated in order to make the rotation A equal to 0. And similarly at B there should be a moment in this direction in order to make the rotation at B also equal to 0. This is how this beam would going to deform. Now this, you can see the direction of the moment is in the anti-clockwise direction, so it has to be taken as negative. Now you can see the slope deflection equation, which is MAB is equal to MFAB plus 2EI by L into minus 3 delta by L. This negative sign is already been taken into consideration. If I have MAB is equal to negative, because of the sinking of support, the bending moment which is getting generated at joint A is negative. So this negative sign should be retained. So what I will do is I will take the delta value as positive value for span AB. That is when the right support is sinking for that beam, for that segment, we can consider the value of delta as positive, as we are required to retain this negative sign, a minus 3 delta by L. So delta becomes positive and the net bending moment which is acting at joint A, MAB as well as MBA will be negative because of the sinking of support or support settlement. Now the value of delta is equal to 5 mm, so I have to convert that in terms of meters. I can say it as 0.005 meters. Now we'll come to slope deflection equation for span AB. For a joint A, I can write it as MAB is equal to MFAB plus 2 EI by L into 2 theta A plus theta B minus 3 delta by L, where theta A I can have to equate it to 0, as end A is fixed and joint A is fixed. Theta A has to be equal to 0. Theta B is an unknown value, needs to be calculated, where delta is the sinking at joint B. Which is equal to minus 28.8 is fixed end moment, plus here the value of EI is not changing and it is constant throughout the length of the beam. I just take the value of EI. I will substitute the value of EI, flexural rigidity given in the problem, as 2 into 10 power 4 divided by 5 into theta B minus 3 into 0.005 divided by span of the beam is 5 meters, which works out to be equal to, on simplification, minus 52.8 plus 0.8 into 10 to the power 4 EI theta B. So now in the previous example, I had expressed equation in the form of EI theta B, whereas here, since the value of EI is given, I have substituted and I have kept it in terms of theta B. If you want, you can retain, you can express the value of equation in terms of EI theta B and EI theta C as well. That's not a problem. But for this component of 3 delta by L, we are required to multiply it by EI and we have to simplify the equation. Only for this component, it is compulsion that it has to be multiplied. You can retain the value of, you can retain you can express in terms of EI theta. And similarly, we'll apply the slope deflection equation for joint B. I will take that as MBA, which is equal to MFBA plus 2 EI by L into 2 theta B plus theta A minus 3 delta by B. On substitution and simplification, I'll get this equation 19.2 plus 1.6 into 10 to the power of 4 theta B. So we have got two equations, MAB and MBA. Now we're going to apply the slope deflection equation for span BC. Now we can say that it is MBC is equal to, again, MFBC plus 2 EI by L. Now if I just write the second span, which is BC, now if I just consider the sinking of support for span BC, the B is sinking, this would going to be, now in order to make the rotation at C equal to 0, the moment should be applied like this. Now the beam would going to deform in this fashion. There would be a moment which gets applied here at joint B. This is 5 mm delta. Now you can see that the rotation moment which are getting generated at joint B and C are in the clockwise direction. Now if I have to make this clockwise direction, in the sense I'll have a positive value of bending moment which are at joint B and C, because for the span BC, for the sinking of support at B. Now the negative sign to be eliminated. If I want to eliminate this, I will make the value of delta is equal to negative. So I can substitute delta is equal to minus 0.005. I'll substitute the value of delta in the equation. MBC is equal to MFBC plus 2EI by L into 2 theta B plus theta C minus 3 delta by L, where delta I'll be substituting it as negative, minus into minus, this becomes plus. So on simplification, we'll get it as minus 2.5 plus 2 into 10 power 4 theta B plus 1 into 10 power 4 theta C. Similarly, we'll apply at joint C for span BC. We'll get MCB is equal to MFCB plus 2EI by L into 2 theta C plus theta B minus 3 delta by L. Again, here also delta has been taken as negative in order to make this component as positive. Now the total bending moment, which is acting MCB, expressed in terms of theta B and theta C, which is 77.5 plus 1 into 10 power 4 theta B plus 2 into 10 power 4 theta C. Now we have all these bending moment values MAB, MBA, MBC and MCB in terms of theta B and theta C, which are needs to be calculated. How we're going to calculate is that we need two equations to solve this value of theta B and theta C. For that, we will go into we'll apply joint equilibrium condition at joint B and C. Now, if I apply joint equilibrium condition at joint B, I can directly say that the bending moment, summation of bending moment at joint B equal to 0, that is MBA plus MBC should be equal to 0. I will write the equation for MBA and MBC. I'll add it together and I'll equate it to 0. On simplification, I can write that 3.6 into 10 power 4 theta B plus 1 into 10 power 4 theta C plus 16.7 is equal to 0. I'll call this as equation 1. And similarly, I'll apply joint equilibrium condition at C. So here we have two bending moments which are acting. Though we have not calculated that with the help of slope deflection, we could directly calculate this value of MCD as minus 40. This is because of the cantilever portion. There are two moments, MCB and MCD, which are acting at joint C. The summation of those two should be equal to 0. We already have developed an equation for MCB. We'll take that, and minus 40 because of the overhang moment is equal to 0. On simplification, we'll get 1 into 10 power 4 theta B plus 2 into 10 power 4 theta C plus 37.5 equal to 0. So now here we have 1 and 2 equation, which we have got two unknowns, theta B and theta C. On solving these two simultaneous equations, we will be in a position to get what is the value of the unknown rotations at joint B and C. So on solving these two simultaneous equations, we get theta B is equal to 0.66 into 10 power minus 4 radians, and theta C is minus 19.1 into 10 power minus 4. So the positive sign indicates that it is a clockwise rotation, or and theta C is an anti-clockwise rotation. And once I calculate the value of theta B and theta C, we can substitute in the slope deflection equation, and we will be in a position to calculate the bending moment values. So the bending moment values on calculation, we will get MAB is equal to 52.275, MBA is 20.25, MBC is minus 20.256. So we can note that it is MBA and MBC summation should be equal to 0. So they are equal and opposite. Similarly, MCB and MCD also should be equal and opposite. We have achieved those values. So the calculation of bending moments are over. Once we calculate the bending moment, we should be also in a position to calculate what are the support reaction with which we can draw the shear force diagram. Now I can split the same beam as I have explained in the previous example. I'll split this into two beams. In the first span, we'll consider both the end moments with the vertical reaction at A as VA and at B as BB1. Now, for the second span, we can see that it is not a simple support, it is a simply supported beam with an overhang. So that also needs to be considered in the analysis while calculating the reaction at VC and BB2. This will be contributing. So now these are the determinate structure. I can apply summation of horizontal vertical force equal to 0 and summation of moment about any joint is equal to 0, we'll be in a position to calculate the reactions VA, VB and BC. VA we will get it as 30.4, VB1 and VB2 will be getting it separately, and adding together we'll get it as 64.66 kilonewton and BC as 84.94 kilonewton. Now we'll be in a position to draw the shear force diagram. VA is positive. We're going to use the sign convention that left up is positive and right down is positive. This is for the shear force. Now we'll take it up, that it is 30.4. There are no loads, it becomes constant. Again, minus the point load which is being applied, it goes to negative sign. And again, there are no loads which are acting from this point to this point, it becomes constant. And again, it is in the upward direction, plus 64, it becomes plus 35. Again, it is constant, and we're going to apply concentrated load at this joint. It goes minus 44.9. Again, at joint C, we have 84 minus 44.9 plus 84.94, it becomes 40. And we have a uniformly distributed load, because of which varies in a linearly varying fashion, and it becomes 0 at free end. Or we know that at the free end, always the shear force also should be equal to 0, and the bending moment is also should be equal to 0 at the free end. So that has to be achieved. Now we have done with the shear force diagram, we'll go with the bending moment diagram. As we have seen that while writing the bending moment diagram, we'll write the end moments over which we're going to superimpose simple bending moments. This is the end moment, which is minus 52.27 and 20.26 for span AB, and minus 20.256 for span BC, which will be over here, and for the span BC, MCB is plus 40. We are plotting it above the reference line. That is, we are going with this sign convention as I have stated in the previous session. And we will going to superimpose simple bending moment, as both span AB and BC are applied with a concentrated load. The variation of the simple bending moment would be a triangle, and we are superimposing the negative bending moment and the positive bending moment, and this portion will get nullified. And here also this portion gets nullified, and this portion will have a negative bending moment. This is positive, negative, it is hogging, and here we have sagging, and this portion will have a continuous hogging. That is, for a cantilever span, because of the uniformly distributed load in the downward direction, the beam would go into hog. Now, corresponding to that, these points represents the point of counterflexure. You can say corresponding points wherein where it changes from positive bending moment to negative bending moment. So here you can see. Now, corresponding to this, here you can see it changes from hogging to sagging, and as approaches the intermediate support, it will going to hog. Again, it sags, and over here at complete portion there is a hogging bending moment, because of which there is a elastic curve impact action. So now on the whole, we have discussed how to incorporate sinking of support in the analysis of continuous beam using slope deflection method. In the next session, we will take up a problem on rigid jointed frame, and we'll see how to apply this slope deflection method in analyzing the rigid jointed frame. Thank you.